Hello, everyone. Welcome. My name is Jennifer Nyman. I am a senior principal at Geosyntech Consultants and the coordinator of the SERDP and ESTCP webinar series. I will be facilitating today's event. This webinar today focuses on DoD-funded research results on advanced modeling tools developed to predict and simulate PFAS fate and transport in Vadose zone source areas at DoD sites. Dr. Jeff Silva and Dr. Bo Guo will discuss how advanced modeling tools can enhance our understanding of long-term PFAS sites and support remediation planning. Each of the two presentations will be followed by a question and answer session. The next two slides provide some instructions for your webinar today. If you haven't done so, you can download Zoom at the link shown here and given to you in your registration email. If you're not able to download Zoom, you can also view the slides using an internet browser like those listed here and by creating a free Zoom account. If you are unable to view the slides or if your screen freezes, try keying Control with F5 to perform a hard refresh. In case of continued difficulties, you can download a PDF of the slides from the webinar webpage and then call into the conference call line provided to you in your registration email. We will also be live streaming the webinar on the SERDP and ESTCP YouTube channel at the link shown here, so that is another option. Today's broadcast is listen only. You can submit questions to the presenters using the Q&A box on the Zoom screen. You don't have to wait until that Q&A period to submit your questions. In fact, it would be great if you submitted questions in advance of that session. When submitting your questions, please add your organizational name at the end of your question. Please try not to submit questions in the chat box. We are going to use the chat box if there are any comments related to technical difficulties. And with that, I would like to introduce Dr. Andrea Leeson, who is the Executive Director of SERDP and ESTCP. Dr. Leeson has been with SERDP and ESTCP since 2001. Prior to that, she was a research leader at the Battelle Memorial Institute, where she conducted research on in situ bioremediation and the design and implementation of innovative biological, chemical, and physical treatment technologies for site remediation and for industrial wastewater. Andrea received her doctoral degree in environmental engineering from the Johns Hopkins University. Andrea, please proceed.
Thank you so much, Jennifer. And thank you as well to everyone who's attending here today. Next slide. What I'd like to do before we go into the technical talks is give you a little bit about information about our two programs. We are two companion programs. The first is SERDP, the Strategic Environmental Research and Development Program. And this is a traditional R&D program where we invest in applied research to secure and support DoD installations. And what we look for is that the knowledge or the technologies that are developed under SERDP at the bench scale can be moved into ESTCP as they mature. ESTCP is the Environmental Security Technology Certification Program. This is our demonstration validation technology program where we can take these innovative technologies or knowledge bases that come out of SERDP and then demonstrate them at the field scale or the operational scale at military installations. Next slide. Our goal with both of these programs is to deliver value to our military installations. We're able to do this in a number of ways, from enhancing mission readiness to cost savings with different technologies we develop, ensuring health and safety, and bolstering chemical and material resilience. Slide 12. We have 6 program areas that support these DoD priorities, and today you'll hear from 2 projects that were funded within the Environmental Restoration Program. Under the Environmental Restoration Program, we're looking in great detail at PFAS in the environment and looking at not only cleanup costs, but also just understanding fate and transport, characterization, etc. We also fund efforts in resource conservation, weapons systems, and platforms. Slide 13, please. installation, energy and water, natural hazards adaptation, and munitions response. And throughout the year, you will see webinars released within all of these different areas. Slide 14. So what we focus on is really funding these critical R&D efforts. The numbers here give you an idea of the program investments, with really over the years, over 3,000 different projects funded in a multitude of different areas that are critical to the Department of Defense. We have been able to fund hundreds of different federal, university, and industry R&D partnerships. And I encourage you, if you'd like additional updates about the programs, about funding opportunities particularly, but also webinars, our symposium, please sign up on our mail list here to get those latest updates. Slide 15. So as I mentioned today, we will be hearing from two projects that are addressing PFAS in the environment. I did want to show you this slide, and we will drop the link to this slide in the chat. It is available on the SERDP and ESTCP website. This is an interactive graphic, and here you can see above the number line are all the different topic areas that we've addressed under SERDP. Below the date line are the topic areas we've addressed under ESTCP. And if you go to the web page, you can click on each of these. It'll take you to another page that will give you a little bit more information about what we funded, and will give you links to individual projects that were selected under that topic area. And from those projects, it will be linked to an individual project webpage where there's even more information. So there's a tremendous amount of information on the website about the various efforts that we funded in this area. Next slide. If you would like more information about our webinars, please visit the link here. This link will give you all of the upcoming webinars. Registration is open. It will also show you how to access archived webinars. Every webinar we've given in the past are also going to be there. And I encourage you to take a look there to see if older webinars would also be of interest to you. Next slide. So at this point, let me turn it back to Jennifer to introduce our speakers for today. Jennifer?
Great. Thank you, Andrea. It's now my pleasure to introduce our first speaker, Dr. Jeff Silva, who is a hydrogeologist. He has worked in the fields of environmental remediation, consulting, and research for over 25 years. He has served as a principal or co-principal investigator on projects funded by SERDP and ESTCP, the Air Force Civil Engineer Center, and the Department of Energy. His areas of expertise include groundwater and surface water hydrology, geochemistry, fate and transport, site investigation, characterization, and groundwater remediation technology evaluation and design. He received his doctoral degree in civil and environmental engineering from the Colorado School of Mines. Jeff, please get us started today with your presentation.
Okay, I'm sorry about that. My mute button went away. Let me get back to the beginning here. Okay. Thank you for coming to the webinar here. I'm going to talk today about some work we did with modifying HYDRUS to simulate PFAS leaching in the Vadose zone. I wanted to add that initially that this work, our current project, stems from a previous limited scope project. The objective, the overriding objective of which was trying to understand these processes impacting PFAS transport in the Vadose zone. And we modified HYDRUS in order to support that evaluation. But as a consequence, ended up developing a commercial version of HYDRUS that can be purchased and downloaded currently. So this particular talk will focus on the model development, and there's another chunk of our work that we're not going to be presenting today, but will be in our final reporting deliverable. Okay, for this presentation, I'm going to start with going over our project goals. And then I'm going to talk about what HYDRUS is, a model, in case people don't know, and the PFAS-specific modifications we made to the model. And then I'm going to go into steps we took to and steps we're going to take to validate the modifications we made to HYDRUS against experimental data. And then I'm going to talk about some conclusions from our work that's based on the model development, as well as what we think are some of the benefits to the Department of Defense. So for our goals, we did modify HYDRUS to allow for PFAS simulation. And this, we pretty much focused on air-water interfacial area adsorption processes in this work. And so as a follow-on from our previous work, our first task was to develop a predictive method for estimating air-water interfacial absorption parameters for the Langmuir-based model that we used to describe that process. And then we went on to develop and incorporate other mathematical models that describe important PFAS transport processes and modify HYDRUS to include those. And then we performed a number of transport experiments to provide data with which to validate the modifications that we made to HYDRUS at the bench scale. And the next step is going to be evaluating the performance of the modified HYDRUS model to simulate leaching at the field scale. So what is HYDRUS? It is, for those that don't know, it's been around for a long time. It started off with the agricultural industry and was quickly adopted for contaminant transport in the Vadose zone in the environmental industry. It is a commercially available unsaturated flow and transport simulator. It simulates transport of solutes and heat and flow, of course, in 1D, 2D, and in 3 dimensions. And so we thought this would be a perfect off-the-shelf platform for simulating PFAS transport in the Vadose zone. So we brought in Yuri Simnek as a co-investigator to help us with this process, and we proceeded to work. I just included the screenshot of the GUI, or the graphical user interface for HYDRUS. For those that have used HYDRUS, I put this in here just to say that although the GUI gets updated periodically, we've not changed anything about the new version of the interface. We just added a module that allows for PFAS transport. A brief summary of PFAS transport in the context of this presentation. The PFAS that we're primarily interested in environmentally is they're large amount of them are surface active, and by that I mean that they interact with interfaces in the Vadose zone environment, and that could be the soil-water interface or Napa water interface if non-aqueous phase liquids are present, and also the air-water interface, and also these interactions with the solid phase absorption-based processes. We're focusing largely on the air-water interfacial processes that impact air-water interfacial absorption of PFAS here. And we're using the Langmuir equation to describe that process. And I put the Langmuir equation here, and I'll discuss it a little more in the next slide. So like I said, one of our first tasks was to develop a relationship to predict these absorption parameters for PFAS that we did not directly measure. And for the Langmuir model, these absorption parameters are the gamma max, which is the maximum surface concentration, as well as the Langmuir coefficient, which is, I guess, the proportionality constant. For the Langmuir coefficient, we used a quantitative structure property relationship based on molar volume. This has been published previously, and it seemed to work out really well for us for the Langmuir coefficient. So we developed this relationship across a wide range of different PFAS. So just using the molecular volume, calculated molecular volume, you can estimate the parameters for absorption at different ionic strengths. But the QSBR didn't work very well for the gamma max term. So what we did there is we adopted a molecular dimensions based calculation approach. It's based on the absorption of an individual PFAS at the interface, at interface saturation. In what area, what size does that, how much area does that take up? This approach worked pretty well for us for gamma max. And so what we ended up with is 2 different relationships that describe, that can be used to predict these absorption parameters for the Langmuir-based model that we were able to validate for linear and branch PFAS, as well as different types of PFAS. With respect to transport, the first thing we did with the model is trying to figure out figure out a way to represent the change in air-water interfacial area as the moisture content changes. And so what we did in HYDRUS was we were using a thermodynamic-based model, or a thermodynamic approach, it's called too. And that utilizes the soil water retention curves, which are represented here for a number of different soil types, and integrating those curves in order to calculate the magnitude of the air-water interface as a function of moisture content. And so that these inputs for the soil water retention curves are needed for the flow model in HYDRUS anyway. So this seems like a logical approach. With full knowledge that in some instances, especially but not at all necessarily instances, the thermodynamic approach can underestimate the areas as a function of moisture content. So with knowledge of that, we went in and applied a scaling factor in the model, user-defined, which is a direct multiplier. And that's what I did here in this bottom chart. I took the air-water interfacial area moisture content curve and then just applied a factor of 3 and a factor of 5 scaling factors. And just to show that the user can make adjustments to the air-water interfacial as needed. I wrote a paper and I came up with an empirical relationship for estimating scaling factors based on surface roughness. There's been more recent work that's been published calculating for a number of different parameters, grain size, saturation, surface roughness, as well as other factors. Regardless of how that's calculated, we've provided a capability within HYDRUS to allow the user to scale the thermodynamic model. With regard to transport, we've introduced a number of different processes. We have we're accounting for nonlinear concentration-dependent adsorption, also concentration-dependent competitive interactions at the air-water interface. This is for multi-component solutions, which in the field you're going to have a multi-component solution. So we needed to account for that. We also introduced a concentration-dependent surface tension reduction capability. And these equations at the bottom are defining the competitive interaction as well as the surface tension reduction. The competitive, you just have different competition for absorption at the interface, but the surface tension reduction, if you have enough mass absorbed, the concentration are high enough at that interface, you can affect the surface tension at that interface, and then you can have some enhanced drainage. So that's what that's accounting for. And so these equations are showing that, just with those two input parameters, gamma max and the Langmuir coefficient, we're using just those two parameters to represent both of these processes. And we also added a first order kinetic capability for absorption at the air-water interface. And this is in response to some of our transient flow models, transient flow experiments that were done by our graduate student. And I'll talk a little bit more about that in a separate set of slides. So we started off evaluating this multi-component model that we put together, and I prepared a number of different solutions to evaluate the validity of the model. And I don't know if you can see this, a little bit blurry, and I apologize, but on these bar charts on the left, we have on the x-axis different PFAS components in each solution, and I prepared, and it's like from increasing surface activity from left to right. So what I did is just have different distributions of PFAS with different distributions of surface activity. And then we diluted these solutions and measured surface tension isotherms, or prepared the isotherms, and then compared the model predictions to not only the surface tension changes, but also the change in total absorbed mass. So what we found is, regardless of the PFAS composition, in these cases, the model is a multi-component model is representing changes in surface tensions appropriately, and also representing the total absorbed mass at the air-water interface. So that was a good early result. And then so we moved forward this is a static case, so this is not under transport. So we wanted to see if the model was representing multi-component transport under flow of transport conditions. So we moved ahead with performing a number of steady state flux unsaturated transport experiments. This is at constant moisture content. We utilize the 8-component solution from the previous slide as the equimolar setup solution, and different moisture contents. And the results here are breakthrough curves. We're injecting from the top constant moisture content throughout the column, taking samples of the effluent, and these are the resulting breakthrough curves. So what we're seeing here is that the model does represent the transport for the non-competitive case. By non-competitive, what I mean is we've reduced the concentration of the individual PFAS as well as the total concentration to a point where we're not expecting, as you would not expect, any competitive results and a competitive absorption between these PFAS. And that's what we saw. You see increased retention with increasing surface activity. You see the models recreating or representing the data very well. And that's kind of a result that we had at the end of our first limited scope project with some literature data that we were able to show. So we're showing this with our own data, and this was a good result. Then we moved on to performing the same kind of transport experiments, steady state flux, constant moisture content, same solution, but we're looking at the competitive absorption case. And how we did that is I increased the PFAS concentration to a point where it would likely promote competitive absorption at the interface. And I kept the remaining solutes the same. And concentrations the same. And what we're seeing is that for the lower, less surface active components, smaller chain, and even the moderately surface active components, we're not seeing any difference in the transport with this higher PFAS concentration. So it's not being impacted by competitive effects. What we do see is that the breakthrough of PFOA and the transport of PFNA is impacted by the larger concentration of the most surface active component, PFOS. It's hard to see it in the next slide. I'll blow this up so you can take a look at it, but you'll have this kind of concentration that's actually coming out in the front that is higher than the input concentration. And then it eventually comes back down and desorbs out of the column as you would expect. And as I'll show on the next slide, at the lower moisture content, we're not really seeing that same effect, but the model's reproducing the results, so that's good. So here's a little kind of closer view of that same experiment here for P4 and PFNA. You see this peak here that kind of comes out very, very early. It's higher. I didn't normalize the axis, but it's coming out higher than the influent concentration, and the effect is more pronounced for PFNA. And so what we think is happening here is you have all the PFAS entering at the same time into the column, and they're absorbing at the interface, and then PFOS will dominate and kick off PFOA and PFNA back into the solution phase. And that provides an opportunity for a concentration effect at the front moving through the column. And so you have more mass coming out early. When you integrate this under these curves to get a mass balance, you get good mass recovery. So we're recovering all the mass. It's just showing up earlier than for the competitive case as for the non-competitive case. We don't see that effect on the lower moisture content case, and I don't know if that's just an impact of effect of not getting enough data resolution to see it, but we'll have to resolve that somehow. Yeah, but the model seems to be reproducing these effects, so we're happy about that. We're ready to kind of put a paper together when we found that another group had already published this, so that's fine. But it's good because they're seeing similar results to ours, and I think for the same reasons. So it was a good result. The next step we took was to take a look at some transient flow conditions, changes in moisture content during the experiment, and therefore changes in the air-water interfacial area. This kind of followed on. So the results you're seeing here is for a 30-centimeter column, same column as the previous breakthrough curves. And what I did here is I started off with a constant flow rate at the rate to maintain a constant, uniform moisture content. Started introducing PFAS, and then at some point decreasing the flow rate and maintaining the same PFAS solution introduction. Then I stopped the PFAS introduction and brought the flow rate back up to its original value, and then let the moisture content distribution normalize and stabilize and become more uniform while taking all these effluent samples. And so when I simulated this initially, I got the simulated result was very different than the experimental result. And then I looked back towards our graduate student, Farhan did a number of experiments at a larger scale, kind of a longer column, 1 meter columns. And she showed that this introduction of this kinetic model, which is a first order, uses the first order kinetics. She was able to represent her field data, her column data very well. And so when I went to her paper, grabbed some of her rate coefficients and a fraction of sites, it's a two-site model. I put those parameters in, and this is the result I got. So at both of these scales, we're seeing this kinetic process at work. Now, the question is whether or not we're going to see this at the field scale. One question. So probably not. Moisture contents here in these experiments, we're changing moisture content very rapidly. So you're changing air-water interfacial areas. So we're kind of really promoting this kinetic absorption process, perhaps. In the fields, at the field scale, moisture contents don't change it very rapidly. So it's likely this will be kind of diminished. But you also have areas of the vadose zone, capillary fringe, fluctuating water table perhaps, or shallow subsurface where moisture contents are changing very fastly, then air-water interfacial changes faster. So you might be able to see it in those instances. But I think the fact that the kinetic model that we implemented is representing the data that we were here in these transient flux experiments is a good validation for that particular part of the model that we changed. Our next step going forward, and this is in progress, is looking at the field scale performance evaluation. We're collaborating with another SERDP-funded investigator using his data for that he performed monitoring at a field scale test cell. Very good data set. We're also working with the next presenter too to kind of refine what we're going to do here. With the goal of determining whether or not the modified HYDRUS can reproduce observed PFAS transport within this test cell. I just included this as an example of HYDRUS. This is something that we did in our first work showing it's just a heterogeneous flow field, different PFAS, PFNA being the most surface active in this site. It's just showing that it's more retained in the shallow subsurface compared to less surface active PFAS. That's a 2D simulation. So in conclusion, we've developed a robust PFAS transport simulation capability within an existing well-known unsaturated flow and transport model. The modifications we made include some key PFAS-specific transport processes related to air-water interfacial absorption. And I want to stress that the model also retains its original capabilities for solute interactions with the solid phase, absorption-based, that would be linear, nonlinear, and also there's flow model capabilities in terms of ideal and non-ideal flow, preferential flow, and all of that. It's all retained. The model has been validated here against bench scale transport data, and its performance will be soon evaluated against field scale data. So for when we think of the benefits of DoD, we have a model that can now serve as a robust numerical tool to support site investigation work for the DoD sites. It also can be used to kind of continue to understand the site-specific PFAS fate and transport processes, and also to support future remedial operations. And just kind of more generally, this work that we've done, the mathematical models and developed, and our testing has greatly improved our collective understanding of some of the key transport processes for PFAS. Wanted to acknowledge my co-investigators, John McCrae, Colorado School of Mines, Yuri Simonek, UC Riverside, and our graduate students, Fran Torres now, she's with EA Engineering, and Sophia Lee, who just recently graduated from the Colorado School of Mines. These are our papers to date. We got several more that we need to publish, and these are available if you want to download the talk. And with that, is there any questions?
Great. Thank you so much, Jeff. To our audience, I would like to remind you at this time to please type in your questions for Jeff into the Q&A box on the Zoom screen. The first question is whether the scaling factor has been implemented in HYDRUS yet, and if not, when will it be?
It is. The current version has it in there. And it's, I should stress too that the current version is, we haven't updated it to include these multi-component competitive effects yet. We're still testing these. And so once we figure it out and validated it, then Jurk is going to go ahead and put that in probably in the next build, but it's up to him. He's on vacation this summer, so. But we'll get that out as soon as it's as soon as we can.
Wonderful. And related to the scaling factors, Are you going to be issuing any kind of guidance or best practices relating to how to implement that and other features that you've been adding?
In the the HYDRUS documentation?
Or otherwise, like in a report?
Yeah, I'm not a representative of PC Progress that I'm not affiliated with them, but what seems to be happening is that as we add things, it's being included in not only the help window in the GUI itself, but also in the documentation. It's just kind of lagging a little behind. I put together a scaling factor approach, and Yurka also publishes the papers in the PC Progress website that people can download. That I have one scaling factor. I think in our final reporting document for this project, we're going to do some comparisons for recently published scaling factor estimates and stuff. So it'll show up there and hopefully in some of the documentation. HYDRUS documentation, the user document. But that'll lag a little bit behind the release.
Okay, got it. Wonderful. Thank you so much. Why was the Langmuir isotherm selected rather than a linear or a logarithmic isotherm? And then also, would Henry's law apply with PFAS, and is it applied in HYDRUS?
The Langmuir was selected because it was one of the models that HYDRUS already has. The actual absorption, we wanted to cover the large concentration range. So as you increase PFAS concentration in the aqueous phase, the concentration absorbed decreases or changes, and so we couldn't use the linear version. I think so we wanted to make it more capable, so we chose the Langmuir model for that purpose in order to describe it. And we got really good fits to a lot of our surface tension data using the Langmuir model. And I know there's a debate between, using Freundlich versus Langmuir and such. I'm going to leave that to those making that argument, but it seems like the Langmuir works for us and works with the transport data that we've seen so far. In terms of, what was the other part of the question?
Sorry. Henry's law. Does that apply to PFAS?
Okay, I'm assuming that means like partitioning into the gas phase?
Correct.
So that right now, HYDRUS does not have that capability. It doesn't. It does in a sense. It doesn't in terms of gas phase transport. It's doing transport of aqueous phase. So it can partition mass into the gas phase, but it's not monitoring its transport. It's basically looking at what it does to the transport in the aqueous phase. So it's not a gas phase transport simulator.
Gotcha. Okay, thank you. Do you have any plans to look at co-solvent contamination, like with TCE?
Yeah, I was just talking about that, and not sure how to implement that. HYDRUS is not a NAPL simulator either, so it doesn't account for a non-aqueous phase. But at the most recent SERDP meeting, somebody answered that question, and I think it can be incorporated. It just won't be. We're not going to be able to define a separate NAPL phase in the model. At the same time, it's very difficult to go out there and characterize the area of the non-aqueous phase liquid water area out in that for a particular site. So it might be a simplification that we're talking about now, but we can we're looking at providing a way of accounting for it.
Okay, great, interesting. We have some questions now about the application of the model to evaluating remedial technologies. Do you have a sense yet with respect to how mature HYDRUS might be for simulations at the field scale?
Well, it's been pretty well validated for the flow model and solute transport, outside of the PFAS realm. So the hydraulics and the mathematics and everything for those kind of things are pretty good. The PFAS portion of it, that's our goal with this this field scale work over at Dix, using that data. And we also have a field site up in Wyoming under an AFCEC funded project that is being done at early next year. So we should have those results for validation, but I'm pretty confident that it'll simulate the results of the field work as long as we can get the right data into it. It's always data driven. So yeah, I'm confident that it'll work. Supporting remedial actions. Basically, it'll help out if you remove all the mass. How long is it going to take for groundwater to stop being contaminated? Those kind of long term forward simulations could be very useful.
Okay, great. What about for something like thermal treatment? Could the HYDRUS model simulate flow and discharge from the Vadose zone at elevated temperatures, like up to 90 degrees C?
That's interesting. I I don't know if it could be that hot. I know it has a heat component to it.
Mhm.
I've not looked into that. That might be a question for Yurka directly, but it seems that it has that capability. It does heat in the Vadose zone, and it also does heat because of like solar heating of the surface or some other things. But I'm not sure about that. But that's a good thing to kind of talk to Yurka about.
Mhm. Okay, great. The next question is from the California State Water Resources Control Board. How does this modeling approach compare with surfactant-induced flow in the Vadose zone?
The surfactant, the tension-driven flow that I was talking about is kind of the surfactant flow type thing. I think it's all a reduction in surface tension that may cause flow. So it's accounting for it. In our transport experiments, we're dealing with concentrations that are low enough that you're not seeing a significant impact. But when you run the simulator, so you can use the simulator to test that. You start increasing the mass of PFAS, increasing the concentrations of PFAS, and you can see this drainage that occurs in the model.
Okay, wonderful. So based on your work, what additional processes do you think are most important that are not included that maybe should be, if there are any, that you would like to include in the model?
I'm trying to absorb what we've done so far, but also, mostly it was dealing with the non-aqueous phase. At first I wasn't quite sure how important this was and how much DAPA would be left, especially if it's hydrocarbon fuels that were used to start these fires. Seems like, though, based on the SERDP meeting, that this is they're coming into the non-aqueous phase liquid. So that would be something to account for in some fashion in this models. So
Okay.
we'll look at that. I don't know if we're going to get to it, but it's something that would be beneficial.
Okay, great. The next question is from EPA, sorry. And it's about whether the air-water interface might move with the water table and whether that is simulated as part of HYDRUS. And I guess that gets to also a broader question of whether these HYDRUS Vadose zone models do simulate the interaction at the water table in the capillary zone.
Yeah, you can. You can have a saturated, it's an unsaturated model, but you can have a water table moving up and down, and then the effect for the changes in moisture content within not within the capillary fringe. That's saturated too, but right above the capillary fringe. So changes in moisture above the water table occurring as a result of the rise and fall of a water table. So you can simulate that.
Okay, great. Next, it's the model applicable for different types of soils. For example, if a soil had high organic matter content that would affect the transport, does the model take that into account?
Yes, that's kind of standard for HYDRUS, so we didn't change anything there. You have to have the right parameters, so you have the right sorption coefficients for the solid phase as well as any kinetics that you see, any slow dilution and such. So you would have to, somehow be informed of what the magnitude of those input parameters would be, either by testing or such, and then input it. But it should represent that well if you have that type of data.
Okay, great. You mentioned using HYDRUS to evaluate remedial actions, and I think you mentioned time frame, but there's a couple questions about whether time can be included within HYDRUS, and or how could HYDRUS be used to estimate the time for leaching or remedial effects, things like that.
Yeah, that's the primary benefit of having these models, is that you can look forward in time over decades, if you'd like, and see what happens. HYDRUS itself is a Vadose model, so you wouldn't be simulating, a plume or something going down here. You'd have to integrate the unsaturated model with the saturated model in order to look at plume dynamics, but you can simulate the input to a groundwater model. And that's been done, with other solutes. And I think it's probably being done for PFAS under SERDP currently. So that's what I would say for that. To that is, yeah. So over time, how many years will it take to get out of the Vadose zone under the conditions that you said? Those kind of questions are what these models are very, very useful for.
Great. Sounds good. And just two more questions for you. First, how is heterogeneity addressed in HYDRUS, if it is?
Yes. If you know what the heterogeneity is, you can have many different, they're called material types in HYDRUS, but and they all have their own hydraulic properties. So you can characterize heterogeneity fairly well. We found, at least at our sites, but the fire training area scale, we're not seeing a whole lot of heterogeneity, seeing layers and such with different soils and stuff. So that's fairly easily, and we're finding that we can represent it in a 1D model, but if you need that kind of complexity, you can go to 2D or 3D and incorporate any kind of pinch off of layers and soils. You just have to define the hydraulic properties for each particular soil type, and then you can include heterogeneity in the simulation.
Okay. Wonderful. And then, Jeff, one last question to wrap up. In all of this work that you and your team have performed, what did you find the most surprising, and what might need more attention?
The most surprising, it's mostly the competitive processes. I wasn't expecting, and the kinetics. I did a bunch of work as a part of this. Is the part that I didn't present. We were looking at absorption at the air-water interface itself, and that's a really fast, instantaneous process. But then we see these connect sites, so that was a little surprising that we've seen it. But maybe that's something that's related to the scale of our experiments. The thing I think that still needs some work is predicting the air-water interfacial area change with moisture content. I think that's still unfinished business. There's been a lot of strides, and we've been trying to figure this out for decades now. But so it's kind of a little bit of a challenge to figure out where that is. And so I think some work on that would be better. I think in Bo's talk coming after this, I know he has an approach at the field scale to evaluate that. So that has some promise in kind of getting us to where we need to be. But I would say that would be something that would need more attention.
Okay. Understood. Thank you very much, Jeff, for your presentation and answering the questions. And now we will move to our second speaker today, Dr. Bo Guo, an associate professor in the Department of Hydrology and Atmospheric Sciences at the University of Arizona. His research focuses on the fundamental physics and mathematical modeling of fluid flow and transport in permeable geological materials, motivated by environmental and energy problems, including the transport of PFAS, shale, gas and oil production, and geological carbon storage. Bo earned his PhD in civil and environmental engineering from Princeton University. Prior to joining the University of Arizona, Bo was a postdoc in the Department of Energy Science and Engineering at Stanford University. Bo, please go ahead.
All right. Thank you, Jennifer, for the kind introduction. So I'm going to present our ESTCP project that we are about to wrap up in a few months. And so the final report will be up early next year. Our project focuses on developing and demonstrating PFAS-LEACH, a comprehensive decision support platform for predicting PFAS leaching in source zones. Okay. I had some trouble moving the slides. So I will start by reviewing some of the PFAS feed and transport processes in the Vadose zone, which Jeff has already covered some of that, so that will save me some time. And then I'll introduce PFAS-LEACH, our PFAS-LEACH decision support platform, and each of the tiered models. I will, in particular, focus on illustrating with examples how the PFAS-LEACH tools can be used to answer practical questions. I'll then finish by concluding, drawing some of the interesting conclusions, and also discuss the benefits to the DoD. Here's a conceptual diagram of PFAS fate and transport in the vadosome and the relevant physical and chemical processes. So in a lot of the ways, PFAS is similar to other contaminant transport, but there are a couple of complications that differentiate PFAS from other contaminants. One is that they have this sort of amphiphilic molecular structure, right? So this carbon chain is hydrophobic and oleophobic, so they don't like water, they don't like oil. And then the head group is hydrophilic. So, when they are put into an air-water system, they would like to hang out at the interfaces between air and water, with the carbon tail being outside of water and then the head group being inside water. That's where they're thermodynamically happier. So because of that, they tend to accumulate at air-water interfaces. Many of them are also charged, so they also interact with solid surfaces, and then the hydrocarbon chain, also because of hydrophobic interaction, they also interact with, let's say, organic carbon. On the other hand, when PFAS are present in pore water and at the interfaces, they also modify the surface tension and contact angle of water, and then can enhance drainage. So they can also, in turn, change water flow. So it's really a fully coupled process, and that involves a lot of dynamics and nonlinearity. So to model these processes, we first need to describe them mathematically, oftentimes using differential equations. And here I'm showing a sort of a set of example equations to illustrate the idea. So like any other contaminants, we first need to solve soil water flow. So we apply three-dimensional Richards equation. The complication is that now the surface tension or the capillary pressure is now a function of PFAS concentration. So we account for that by scaling the capillary pressure or water pressure with the surface tension and contact angle, cosine of the contact angle. For the transport, you would write this advection dispersion equation like you were solving other solutes, but now you need to account for this partitioning to the solid surfaces and air-water interfaces. And here we have included this non-linear and rate-limited solid phase absorption. So you have this two-side. We have also included this multi-site model, and then non-linear and rate-limited air-water interfacial absorption. Here we're using Lambier model to model the air-water interfacial absorption. And then you have also the kinetics included. So again, these are just example set of equations. There are other complexities that are included in our model, but I just want to use these equations to illustrate the idea. For example, multi-component transport and competitive absorption are included. So incorporating all of these three-dimensional fully coupled differential equations with the surfactant-induced flow, long-linear and rate-limited absorption, and other complications like multi-component transport leads to this most sophisticated tier 1 model, right? So here you can see that we've put this 4 tier of models under PFAS-LEACH with these 2 axes. The horizontal is model complexity. The vertical axis is computational cost and input parameters. So on the top right is the most sophisticated tier 1 model that includes all of the processes that we're now currently able to include. And then tier 2 is a 1D simplification of tier 1. Our original plan is to implement this in the open source version of HYDRUS, but then we decided to actually code up a one-dimensional numerical code from scratch that will also make it open source. Tier 3 employs further simplification, such as steady-state infiltration or linear absorption, which allows us to derive analytical solutions to these partial differential equations. And tier 4 is a direct revision of the simple EPA dilution attenuation factor approach to incorporate PFAS partitioning to air-water interfaces. So tier 3 and tier 4 are implemented in Excel spreadsheet with graphical user interface, and they are already now publicly available. Tier 2 will be made available, the beta version will be made available at the end of this year. And then tier 1 will be made available around March next year. I forgot to mention, so there's also a user guide accompanying these tools that demonstrate explaining how to determine parameters and how to select different type of processes to model, and then also, with examples showing how to apply these models. Over the years, we have validated these PFAS-LEACH models by a wide range of column experiments. Column type transport experiments conducted for individual PFAS, PFAS mixtures, and mixtures with hydrocarbon surfactants, steady state and transient flow conditions. I will not talk about those in this presentation. Instead, I will focus on illustrating how PFAS-LEACH can be used to answer sort of more practical field relevant questions. And even for that part, there are several papers that we developed within this project that I will not be able to cover. For example, the impact of preferential flow and dual permeability, dual porosity formulations. Those you can find them in the publication list of our project page. So I'll start with tier 1. I'll present 2 examples. The first example will illustrate the impact of groundwater fluctuation on PFAS-LEACH, and this was asked in Jeff's presentation earlier. So as we can imagine, actually, as we know, many of the sites, the groundwater table is not static, right? They actually fluctuate over time. And one common fluctuation is this seasonal fluctuation driven by, let's say, variability in recharge. And when the groundwater table fluctuates, they periodically collapse and restore interfaces in this fluctuation zone. And this could actually have a lot of interesting processes. For example, when water table rises, they destroy interfaces, and then the mass of PFAS is kicked from the interface to the pore water. And then when the water table falls, then you form new interfaces, and then you basically strip the mass of PFAS from the pore water and the solid surface to the air-water interfaces. And this has implications in terms of PFAS leaching in the vadose and the mass discharge to groundwater. So we've conducted a series of simulations, and here I'm going to show just one simple set of example results to illustrate the concept. So here we simulated the change of water saturation, air-water interfacial area, and then the mass fraction of PFAS in the aqueous phase, air-water interface, and solid surfaces. Now, when in the beginning, the water table is at the bottom, and then it goes up and then goes down. You can see that the water saturation, of course, in the fluctuation zone increases, but also above the fluctuation zone increases, okay? And then because of that, the air-water interfacial area drops dramatically. Both in the fluctuation zone, of course, drops to 0, and then above the fluctuation zone also drops dramatically. Now, these processes drive the mass redistribution of PFAS between aqueous phase, air-water interface, and solid surfaces. So you see that when the water table rises up, you have much more pore water mass in the pore water, and then also in the solid surfaces. Okay, and this basically enhances the leaching vertically, because only the mass in the pore water is available for leaching. And not surprisingly, we also found out that actually also influences lateral flushing, because the fluctuation zone has a strong lateral flow velocity following the groundwater. So that also enhances the lateral flushing. So in other words, if you use a one-dimensional model, even if you account for the fluctuation, you wouldn't be able to capture that horizontal or lateral flushing due to this fluctuation. The other implication with this fluctuation is that because it destroys interfaces in the fluctuation zone and partitions the mass of PFAS from the air-water interface to the aqueous phase, so they also lead to strong temporal fluctuation of PFAS concentration in groundwater. So, for example, these are the simulated groundwater concentration of PFOS in groundwater well next to this source zone. So you can see that the groundwater concentration changes dramatically over time. And in fact, they also strongly correlate with the groundwater table. When the water table goes up, they increase, and when the water table goes down, they drops. And the maximum over the minimum concentration during this period of time can be up to 20 times. So what does this mean? This means that when you sample PFAS groundwater concentration, it will be a good practice to sample multiple times, at least over a year, to obtain representative groundwater concentrations, especially for this longer chain that are surface active and that could be driven strongly by the groundwater fluctuation. So, okay, so the previous simulations were conducted for a homogeneous vadose. What about heterogeneity? And in fact, I mean, the answer is actually very simple. So the enhanced leaching that we saw earlier is greatly reduced in heterogeneous vadosomes. And this is actually a very interesting story. So we conduct two sets of simulations without groundwater fluctuation and with groundwater fluctuation. And here we show the groundwater concentration without table fluctuation. And you can see that actually the background gray lattice represent the preferential flow pathways that have greater pole velocity. So you can see that much of the PFOS is in the preferential flow pathway as we expect. And then we now take the simulation with fluctuation and subtract by the one without fluctuation. And we can see that we can sort of see how the mass moves with fluctuation. And we found out that the mass that originally in the preferential flow are now moved to these sort of slower zones by lateral flushing. So basically what happens is that during this, when the groundwater table goes up, you have lateral flushing. The PFAS that was in the preferential flow was flushed into this slower flow zone that has much greater air-water interfacial area and then have, of course, greater retention capacity. So sort of PFAS are somewhat locked in those slower flow zone and then reduces the sort of the flushing of PFAS into the groundwater. So this was a very interesting finding, just by running these sophisticated models and then designing the scenarios in a way that we can sort of isolate these different factors. The other example is about surfactant-induced flow, and the questions that we're interested is that when HFF is applied, even if diluted, their concentration is quite high. And we would like to understand whether surfactant-induced flow lead to strong lateral spreading of the applied HFF solution. And then the second question is that if you have this surfactant-induced flow, would that enhance or reduce PFAS leaching in the vadose? So to answer this question, we conduct a series of simulations. Here I'm going to show just a couple of illustrative results. So here, basically, what we did is that we simulate a two-dimensional simulation with a surfactant-induced flow, and we basically count the mass of PFOS that goes outside of the domain. Okay, and then you divide by the total mass, and you get a fraction of the mass that's going outside of the domain. And you can see that it's about 2% after like 80 years. And in fact, this spreading, most of that is due to dispersion, not due to surfactant-induced flow, because this spreading is still there, even if we turn off surfactant-induced flow. So this shows that the lateral spreading is minor. And then again, we also compare the vertical leaching for the one-dimensional model, two-dimensional model with and without surfactant-induced flow. And for these scenarios that we simulated, there's not a big difference. You see some local changes, but if you look at the long-term leaching, it's really have a minor impact on PFAS leaching. So why is that? The reason is that HFF solution, when it's applied, is very high, but once it enters soil, much of the mass goes to the air-water interfaces, sort of it's stripped, and then the pore water concentration is much lower, and then the change of surface tension is also correspondingly also lower. And the implication of this is that in the field, perhaps you could simplify these processes, and by decoupling the flow and transport, although it's disappointing scientifically, but practically is actually very helpful because we can now make a bunch of simplifications. So now I'm going to talk about tier 2. The tier 2 model, we have applied that to simulate PFAS leaching at an HFF impacted site. So this site was really a well-studied site by Charles Schaefer's team in one of the SERDP project. And you can see that in this around 4x4 meter test cell, it was in, many instruments were installed, lysimeters, suction lysimeters, soil boring, soil moisture probes, multiple of them are installed. So we can, they are really able to get a lot of data sets. And we see that this as a great opportunity to test our model. So for example, I'm showing the moisture data during the ambient infiltration, and also there's a second period of experiments where they have a enhanced water flushing. And so we are going to use this data to test the model under these field conditions. And so we've done a bunch of calibration and validation to figure out the hydraulic parameters of the soil. So we use the ambient infiltration to calibrate the moisture simulation, and then we use the enhanced flushing period to validate. You can see that the model validation match quite well with the data. Now, once we have some confidence in the soil parameters, we then obtain all of the parameters of PFAS absorption, etc., and then we run in a predictive mode to predict pore water concentration, okay, over time. And now we contrast that with the sampled pore water concentration from the lysimeters. So you'll see that we actually run two sets of simulations. One is that we account for the rate-limited solid phase desorption, and one we do not. So you can see that when we account for the solid phase desorption, the simulation is much closer to the pore water concentration that we predict. So this suggests that at least during this time scale of pore water sampling, the rate-limited desorption appears to be important. The other thing that we did is that once we have confidence in the model, then we start to run long-term simulations to simulate the leaching of PFAS. So we ran simulations of PFOS, taking that initial soil profile as condition, and we simulate over time. So PFOS simulation is consistent with the field data. Much of the mass stay in the shallow subsurface after several decades. Okay, and this is consistent with what we saw earlier in other sites. Now, what surprised us is this PFHX. If you do the simulation, much of the mass is gone about like 20 years, less than 20 years, about 10 years. But if you look at the field data, this is after a couple of decades after the contamination, most of the mass, this is log scale, right, still in the shallow subsurface. So this is a surprise, and we have formulated a couple of hypotheses. And a working hypothesis is that it's likely due to precursor transformation, continuously generating PFHXS at this site. That is currently not incorporated in this simulation that we run. So an interesting thing out of this project is that we also figured out a sort of an approach to leverage this pore water concentration to quantify PFAS leaching. So what you could do is that you assume that the mass in the soil comes from the pore water, solid surface, and airwater interfacial absorption, and then you rearrange. You can basically obtain the airwater interfacial area if you know all of these parameters, okay? Or you can estimate them. So if you have soil concentration with moisture and with this estimate of these parameters, then you can actually estimate airwater interfacial area by using the pore water lysimeter concentration. And this approach has been implemented in Tier 3 and Tier 4, and will also be implemented in Tier 1 and Tier 2. So the last example I will discuss is Tier 3 and Tier 4. So again, Tier 3 is this analytical solution, one-dimensional, that assumes steady-state infiltration, okay? But it solves transient transport of PFAS, accounting for advection dispersion, as well as partitioning to the airwater interface, to the solid surface, and rate-limited solid phase absorption. We're also incorporating, in this simplified case, the rate-limited absorption to the airwater interfaces. So just to clarify, in the Tier 1 and Tier 2, they all include all of these rate-limited processes. But Tier 3, we have to make some assumptions to be able to solve them analytically. So, for example, in the original version, we did not account for rate-limited airwater interfacial absorption, but now we're also accounting for that even for this simplified version implemented in Excel. So in this Excel tool, it's available in this on GitHub from this link, and we actually designed 3 modules, sort of with increasing sophistication and capacity. The module 0 is the basic module sort of for quantifying PFAS leaching and deriving SSL. The module 1 has this additional capacity to do parameter sensitivity analysis, because oftentimes our parameters are uncertain. So we would like to have this capability to sort of understand how the parameters influence your results. And module 2 is this sort of most advanced module among the 3 that allows users to do Monte Carlo type uncertainty analysis. And these we're still finalizing that, but it will be available next Monday. Okay, so here is the sort of the user interface for module 0 basic analysis. It has different compartments for you to input site information, soil parameters, PFAS parameters, groundwater dilution information, initial soil profile. It can take in any arbitrary soil profile, and then lysimeter data. If you have them, you don't have them, that's fine. There are also approaches for you to do that without them. And then there's simulation information using the basic solver, assuming equilibrium, and then advanced solver that accounts for rate-limited desorption for both solid phase and air-water interface in the future release. For now, it has the rate-limited solid phase desorption. It also has a user interface for the output, so you can, has drop-down menu. You can look at different results like vadose zone mass discharge rate, mass remaining in the vadose zone, sort of for you to evaluate source strength. And then PFAS concentration in a receptor well on the edge of the source zone, and soil concentration profile in the vadose zone, and aqueous concentration in the vadose zone. It also provides the capability for us to directly derive or compute soil screening levels, okay? And for this tier 3 and tier 4, and also the standard EPA approach. And you can, have all the SSLs computed simultaneously. And there's a user guide that explains all of the stuff that I talked about. And, of course, we're also receiving a lot of feedback from the community. And thank you for those who have provided feedback that really help us to improve the tool and also the user guidance. Now, module 1 basically allows you to do sensitivity analysis. You can change the parameter to have a lower bound, upper bound, and then you can run the simulations together. So you sort of see the range of possibilities in your site. Here I'm demonstrating sort of the sensitivity to net infiltration, but you can also do sensitivity for the other parameters. The module 2 has this Monte Carlo simulation capability that allows you basically to sample from a distribution of your parameters, either log normal or normal distribution. And then you can define how many number of Monte Carlo simulations you want to conduct. And then from that ensemble, the simulator provides an upper bound and lower bound of discharge, receptor well concentration, as well as soil screening levels, right? So that is handy in terms of quantifying uncertainty at your site. With that, I would like to conclude. So PFAS-LEACH provides a suite of models across different levels of complexities for simulating PFAS-LEACH in the vadose zone. And the models account for the primary processes influence PFAS migration and retention in the vadose zone. In particular, the tier 1 and tier 2 really account for all of the processes that we're able to formulate and to parameterize. And tier 3 and tier 4, we have to make simplifications, and then of course we also evaluate the applicability of those assumptions. And PFAS-LEACH have been validated by laboratories results as well as field observations, and demonstrated to be effective tools for various site management purposes. We envision that the PFAS-LEACH models really can be effective tools for assessing source strengths and PFAS risks to groundwater at field sites, and determining soil screening levels that are protective groundwater at PFAS impacted sites, and designing and optimizing remedial objectives and actions. I would like to acknowledge my co-PIs, Mark Brousseau, my colleague from the University of Arizona, Chris Higgins from Colorado School of Mines, and Jim Hatton from Jacobs, and also members from my group, Jisai Zhen, Jacob Smith, Ryan Russell, and Mima. Some of them, Jacob and Ryan have graduated now. They're now in the consulting business. And there are a list of papers that are relevant to the presentation today. but there's also a complete list of publications that I did not talk about, but you can find them in the project page on ESTCP's website. With that, I would like to thank you and happy to take any questions.
Great, thank you, Bo. And to our audience, now is a good time to go to the question and answer box, type in your questions for Bo. Bo, you talked about the field scale simulation. Can you describe how many parameters were calibrated using the field scale data and how many parameters were specified more independently, or at least approximately?
Yeah, so I think they were referring to the tier 2 example application at the PFAS-impacted site. So that is actually a research site. So we have a lot of data. And for the soil parameters, the hydraulic parameters, this Van Nuchten, this KSAT stuff, we calibrated using the moisture data, but then we also validated using the second period of moisture data conducted at the site. And for PFAS transport, actually all of the parameters were determined a priori. So there was no parameter calibrated.
Excellent. Okay, great. Thank you. Next, could you please discuss the relative effects or the magnitude of the effects on transport of air-water interfacial partitioning versus the soil-water partitioning and dual domain transport?
So can you repeat the question? Is that to sort of comment on the relative importance?
Yes.
That's a good question. So for the longer chain, for the longer chain PFAS, air-water interfacial absorption, of course, is quite important. But then it also depends on the soil properties, right? So if you have a super high organic carbon content, or you have a lot of clay and silt, then solid phase can also be important. But in general, when you go deeper in the subsurface, let's say below 1 meter, normally organic carbon is relatively low. So at that depth, I would say for this longer chain, air-water interfacial absorption is definitely more important under most conditions. And for shorter chain, both air-water interfacial absorption and solid phase absorption are less important. Okay, but these are anionic PFAS, that we have simulated, and there are also cation and zwitter ionic PFAS that are commonly observed now at the sites, so they can be positively charged. And for those PFAS, the solid phase can be very strong, because soil surfaces many of them are negatively charged. So for those PFAS, it remains to be evaluated the relative importance. But I would expect that the solid phase absorption would be much more important than let's say anionic PFAS.
Okay, great. Thanks. That's really informative, and of course, it differs depending on the PFAS. The next question is from California Department of Toxic Substances Control. Can you describe the approximate concentrations of PFAS that might be needed to affect the properties of the air-water interface? I think this question is getting at whether the concentrations we see at contaminated sites would affect those properties.
Yeah. So I think, based on what we found, and, you can see from the simulations of the surfactant-induced flow, what we are saying is that under many of the sites, the pore water concentration is relatively low, and they in general do not have a huge impact on this interfacial tension. And even if they do, the overall impact on this long-term leaching of PFAS is minor. Okay. That's based on the results that we have seen. It remains to be tested at sites, but the pore water concentration that we simulated are consistent with the ones that are sampled by lysimeters. It's usually on the single-digit milligram per liter. So that's sort of my answer. They are not super relevant under field conditions for many of the sites. There are some exceptions, but that's our understanding at the moment.
Gotcha. Thank you. As you're aware, AFFF has some pretty unique properties like non-Newtonian behavior, viscosity differences, foaming, etc., that might influence infiltration. Have you considered AFFF specific effects or multi-phase flow effects into the model, or will you?
Currently not. I actually come from this fluid mechanics and multi-phase flow community, so I did my PhD in that area. First of all, it'll be rather difficult to do that. There's a lot of thermodynamics you need to figure out to describe the behavior of AFFF. But on the other hand, again, right, under these environmental sites, the concentration are relatively low. When the AFFF are released, their concentration is high, and you have this rheological effects. But once they enter soil after decades, the concentration drops significantly due to absorption to airwater interfaces. So we would claim that they may not be as important, but of course, this is scientifically should be evaluated. But based on the time scales and the range of parameter space that we explored, they are likely not super important under field conditions.
Okay, great, thank you. In your examples, it showed that it might take hundreds of years for the Vadose zone to become depleted of at least some PFAS. Have you considered whether there are options for enhancing the mass discharge enough to clean up a site in a shorter time frame? How can this tool be used to optimize?
Yeah. So there are few options that are actually explored by our colleagues in the SERDP and ESTCP community. One of them is soil washing. So you could apply soil washing and you collect the enhanced, sort of leaching at the bottom. And so these tools, for example, can be used to evaluate, sort of design the remedial objectives, right? So you can run different infiltration, you can see how fast you can remove, and you can design your strategy. At least that one of the ways that it can be used. And of course, we're also open for the community to explore other approaches to creatively using these tools.
Okay, great. The next question is about the KOC values. The audience member notes that many PFAS models rely on laboratory-derived partition coefficients, but there's been research about discrepancies between lab-based and field-measured KOC values. So how do you recommend that be handled at a site?
So for that particular problem, that project, so Charles Schiffer's team collected those field soils, and then they measured those FOC in the lab, and we used those FOC to determine. Oh, sorry, you're asking about KOC. Okay. I think the KOC, the variability between lab and field might be due to the specific organic carbon, right? So different organic carbon can have different KOCs. I don't really have an answer to this question, but one possibility is that if you know the range of KOCs, then you could use, let's say, the sensitivity module or Monte Carlo module to evaluate the impact of that uncertainty on your results. I need to think about how to, in addition to that, how to sort of narrow down this discrepancy, but at least you could account for that in your results.
Okay, great. Yeah, good point. Thank you. And next, how sensitive are the results to dispersivity, given its dependence on transport distance?
Yeah, dispersivity is actually an important parameter for PFAS transport in the Vadose zone. And if you see that you could actually test that also in the simulators. So it is a relatively important parameter. And then of course, we would recommend that you conduct sensitivity analysis on that.
Okay. Excellent. And now, Bo, just to wrap up, would you please summarize the next steps in this work and how these tools will be available for folks?
Yeah, so for this project, we pretty much have finished Tier 3 and Tier 4. And we're finalizing this Monte Carlo module, which we're working very hard to make it available next Monday. And then we're scheduled to release the beta version of Tier 2 at the end of this year, and then Tier 1 early next year, like around March, April. And then that would pretty much conclude the project. But then we're also extending this project, these PFAS-LEACH tools to incorporate other processes that are important we welcome feedback from the community. We have been receiving a lot of feedback for our tools so far, and we would welcome more feedback. If you have any ideas of what process could be important, we would like to hear them and would like to see if we can implement them. And for example, precursor transformation, we see that it was important, and so far we have implemented it, but we don't have parameters to parameterize that. The reaction pathways and rates, etc.
Got it. All right. Thank you, Bo. Thanks to both of our speakers today for the very informative presentations and answering the questions. To our audience, as a reminder, you can visit the SERDP and ESTCP webinar webpage to register for the upcoming webinars. And before we conclude, I just want to remind you both the audio and a copy of the presentation of today's session will be on the webinar webpage in case you would like to refer to them in the future. We would appreciate it if you could please take a moment to complete the survey that will pop up on your screen at this time. And this concludes today's webinar. Thank you.